In the second part of our example, we'll look at the um, inductor current, and specifically we are interested in calculating the ripple of the inductor current. So here you can see the inductor current in a boost converter. During the on time, so when t is between 0 and d times switching period, the inductor ramps up with slope of m1. And from the relationship between inductor current and voltage, we know that the slope is, uh, which is basically the time domain derivative of the current, is the ratio of the voltage applied to inductor and the inductance. So during on time, this ratio is, we just calculated the voltage that's applied to inductor, VL, it's VI minus IL times RL plus R1 divided by the inductance. And we have a similar equation for the slope of the inductor during off time. Please note that this second slope, the down slope, is negative. That's why the inductor current goes back to the same point where it started its current in the beginning of the cycle. So now we know the average of the inductor current and we know the up slope and down slope. So we can calculate the peak-to-peak ripple of the inductor. So let's look at that. The average of the inductor current is the load current divided by 1 minus d, or d prime, and with the duty cycle that we calculated earlier from the plot, this turns out to be 745 milliamp. So in order to deliver 120 milliamp DC current to the output, we need to draw an average current of 745 milliamp from the input, which is delivered through the inductor. So knowing the average inductor current, we can calculate the slopes. And just plugging numbers in equations that I showed you earlier in previous slide, M1 turns out to be 0.7 ampere per microsecond, and M2, the downslope, is minus 3.6 amperes per microsecond. The peak-to-peak ripple is the difference between this highest point and lowest point, and that's M1, this slope, times the time that this upslope lasts. And also we can say that it's the difference between this point and this point, and we can use the off time for this calculation. So it's M2 times the off time, which is d prime times switching period. Well, we need an absolute value for this because M2 is negative. Anyways, the peak-to-peak ripple current turns out to be 580 milliamp. So think about 580 difference between highest and lowest, an average of 745 milliamp. So an interesting question to ask here is that for what value of the load current the inductor current touches the x-axis or becomes zero for a very short period. This is very important in analyzing DC-DC converters in general, and this is the boundary between continuous conduction mode and discontinuous conduction mode. There are major differences in terms of steady state operation and also transient behavior of converter depending on CCM or DCM operations. So we need to know before design that for which load currents we are operating in DCM and for which load currents we are operating in CCM. Fortunately, this boundary can be easily calculated by just looking at this geometrical view of inductor current. We know at the boundary the minimum value of inductor current should be 0. This means that the peak-to-peak ripple current should be twice of the average current. So this equation here, the average equal to half of the peak-to-peak ripple, is a kind of a universal definition for the boundary between CCM and DCM. And we know the equation for average inductor current and also the ripple current, so we can calculate these two numbers. If the average is higher than this half of peak-to-peak ripple, the inductor is in CCM. In other words, it's in DCM. For example, in our calculation, we know the average is 745 milliamp and the peak-to-peak is 580. So 745 is higher than 580 divided by 2, which is 290. So we operate in CCM with a lot of margin. Second question is, when is the boundary point? And if we solve this equation, turns out that the critical load current at which the inductor current becomes zero for a very short period can be calculated from this equation. And this is 32 milliamp of current from the load. So right now we're using 120 milliamp load current. If we drop it to 32 milliamp, we enter discontinuous conduction mode.